Yeah. Oh, there. I guess for that. Oh, the winning plan. I think that's nice. I say my legs and read like once we it's a pretty time something.
Which one? Oh, yeah, I'll have a receipt, but yeah, I got some.
All right, it's 4 o'clock. Let's go and get started. All right, good evening, everyone. How's I guess still afternoon. How's everyone doing today? Good to hear. All right, so I graded your guys' homework ones yesterday, so you guys should see the grades on Canvas. So overall, you guys did fantastic. You guys did great. So you guys, either your Math 250B professors did a great job, or maybe the questions were too easy. So no, I'm just kidding. I'm not gonna make the questions harder. So homework 2 is up. So after today, you should be able to do the majority of it. So I'm hoping to finish up all of second order ODEs today. Today we're going over a specific topic called undetermined coefficients. Maybe you've seen this before in your previous math class as well, but this is a method for solving non-homogeneous second order ODEs. Okay. So we'll be going over that method today, as well as kind of the physical application of this as well. Specifically, what did those non-homogeneous terms represent? and how they can be kind of dangerous too. And so what I'm hoping to end with today is a phenomenon known as resonance, what that means, and why you usually want to avoid it in your engineering systems. All right, any questions I can answer before we get started for today? Okay, all right, so let's go and get started. Okay, so topic for today is non-homogeneous linear second order ODEs. The names of these all these things are always so long just because yeah, we're working on the kind of a specific subset of these second order ordinary differential equations. Okay, so far, we've only been solving what are called homogeneous equations. Okay. If you wanted to be technical, technically we've been solving second order linear homogeneous equations with constant coefficients, but we'll just focus on the homogeneous part. Okay. And so they look something like this. So we have d squared y dx squared plus p dy dx plus q y is equal to 0. Okay. All right, so we've spent a good amount of time solving these equations here. And even last class, we talked about probably their most common physical application, which is through analyzing a mass string dam. Okay. So we've done this, almost maybe a dozen times at this point. You would form the characteristic equation from this. You would solve for the roots of the characteristic equation. And, based on the roots of the characteristic equation, that would then form your solution. Okay. But we've only done this for homogeneous equations. And if you recall, all homogeneous basically means that the right-hand side of this equation is equal to 0. Okay. All right, so today we're going to lift that assumption. And so we're going to consider cases now where this is non-zero. Okay. And so instead of this whole thing equal to 0, now this is all going to be equal to some arbitrary function of the independent variable. Okay, so that's going to be called R of x. Okay. So one key point here is that this right-hand side function should not include y at all, and so it's only a function of x. Okay. I'm starting to understand a bit more why no one wants to teach in this class at this time every week. Lots of weird noises that happen occur on each side of the walls. They gave me this class like, oh, this is a great time for this class, and it's in this room. It's a nice cozy room, but I can understand why no one wanted this room. Okay, so this is only a function of the independent variable. So remember, the independent variable that we have, usually it's x, but sometimes it could be t as well, right? If there is the dependent variable there, if y is there, then that's not a non-homogeneous term. That should be part of the differential equation on x. Okay. All right, so before we get into methods on how to solve this, let's talk about some of the physical, I guess kind of the origin of why this term comes into the equation, because usually this non-homogeneous term plays a very important role, a very clear role in a lot of these physical systems. All right, so usually the non-homogeneous term usually that non-homogeneous term represents some kind of external input or some kind of external forcing into the system that's going to cause the system to respond or react. So it's separate from the physics of the system. So it's not represented by the physical properties of the whatever system you're analyzing, but some kind of external effect that will cause some response. Okay. So the most classic example of this. So let's look back at our mass spring damper, just because that's kind of the easiest to visualize. Okay. So a mass spring damper is represented by a mass connected to a spring and some kind of dash pot. Okay. Right. So we analyzed this system in isolation last time, right? And so we got the homogeneous solution to these ones. But oftentimes these systems are subjected to some kind of external force, right? So let's say that you have this mass spring damper, it's sitting on your table, and then you take your hand and you just push it forward with your hand. Okay. So you apply some kind of force this way. Okay. And in particular, let's say that you're going to take that force and you're going to vary it with time. So you're going to push it forward, maybe pull it back, push it forward, pull it back, right? So this forcing can vary with time. So this force represents some kind of external, it's an external force basically, right? It's something that isn't inherently part of the mass spring damper, but it is something external that's going to affect its behavior. Okay. So this external force, the way we can represent its effect mathematically on our system is by including it as a non-homogeneous term. So as we kind of go through the lecture today and we kind of see the different non-homogeneous terms, I want you guys to kind of keep this in mind that each of those non-homogeneous terms represents some kind of external effect, right? Something that wasn't part of the system or not part of the system originally in isolation, but it's something external that you can apply to the system that's going to cause some kind of response. Okay. Sometimes in some literature, this non-homogeneous term is sometimes called the input to the system. Okay. Because oftentimes, if you have a physical system, usually it's not going to do anything, or it's not going to do anything exciting unless you provide some kind of input or some kind of force. Okay. Okay. So that's what the non-homogeneous term represents. Okay. Now, how do we go about solving these types of equations? Well, we basically have to solve another problem. Right? So, kind of the most generally accepted way to solve these is to solve basically two problems kind of at the same time, or two problems kind of one after the other. Okay. Okay. So let me kind of write the two steps here. So step one is to actually solve the problem exactly in the same way that we've done before. So step one is to solve what's called the homogeneous part of the solution. So that part is actually exactly as we've done before. So you're going to form the characteristic equation, find the roots of the characteristic equation, and then form your solution based on that. And if you do this part right, there should be two arbitrary constants in your homogeneous solution. Okay. Now, of course, to do this, we can only do this if the equation is homogeneous. And so for this part of the solution procedure, you're going to pretend the non-homogeneous term is gone. Okay. So step one to solve this problem is to just, pretend it's a homogeneous problem and just solve it like normal, okay? So this is going to give us what I call YH, okay? So YH is going to be what's called a homogeneous solution, okay? All right, step two. So once you find the homogeneous part of the solution, then you have to solve for what's called the particular solution. And the particular solution, this is where the non-homogeneous term will start to come into play. Okay. All right, so the particular solution is going to give us another solution to the problem. So we'll call that YP, or Y particular. Okay. And so part two here is going to be the subject for today. So that's exactly what we're going to do, is we're going to learn how to solve for particular solutions. Okay. Now there's multiple methods for doing so. You might have learned those multiple methods in your previous class, but for this class, just kind of based on the interest of time, and just because this is going to cover probably most of your practical situations anyway, we're going to focus on a method called the method of undetermined coefficients. Okay. All right, and so once you've applied that method, you have your homogeneous solution, you have your particular solution. Your final solution, or your full solution, is just the sum of these two parts. Okay, so we have y of x is equal to YH plus YP. And if you have any kind of initial conditions, if those are given to you in the problem, you would apply that on the full solution. So this is something that gets confused a lot of the time, because a lot of times when you have a non-homogeneous problem, people apply the boundary conditions or the initial conditions on just the homogeneous part. But when you have initial conditions, you need to include the particular solution as well. Okay. Okay. All right, so that's the game plan for today. So, for today, we're going to be focusing on, the method of undetermined coefficients. We're going to do a few examples on that just to see how that's done. And then, we'll combine it together to solve for full solutions to, these non-homogeneous problems. Okay. All right. Any questions on kind of any of this so far? Okay, good. All right, so let's talk about undetermined coefficients. Okay, so the method of undetermined coefficients is kind of not really a method. It's kind of it's a little bit kind of little bit disrespectful to the other methods to call this a legit method. It's more of a trick, right? So the trick with undetermined coefficients is to say that, our particular solution should have the same functional form as our non-homogeneous terms. And so the operative keyword here is the same functional form. So whatever type of function your non-homogeneous term is, then your particular solution should have that same form. So for instance, if your non-homogeneous term is a polynomial, that means your particular solution is probably going to be a polynomial as well. If your non-homogeneous term is a sinusoid, then your particular solution should probably be a sinusoid as well. Okay. Okay, so of course, this only works for a certain subclass of functions. And so, this only kind of really works for some of the more common functions out there. Okay. And so we're going to use this for exponential functions. We're going to do this for polynomials. Sines and cosines. And any combination of the above terms. Okay. All right. So that's really all there is to undetermined coefficients. It's just whatever form your non-homogeneous term is, your particular solution is going to have that same form, with one caveat. So the caveat is that, even though it may have the same functional form, the coefficients in front of each term are unknown, right? And so you have to plug in to solve it. Okay. 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 So I think the best way to kind of illustrate this is just kind of through an example. And so, there are kind of patterns that we can come up with and kind of tables and things that we can all do. But I think just doing an example, I think is just kind of a fast and easy way to just kind of show how it's done. Okay. Okay, so let's do kind of a very simple example here. Okay. And for this one, we're going to solve for the full solution. So you'll see kind of the whole shebang. So you're going to see me solve the homogeneous part and then the particular part. Okay. All right, so let's say we have d squared y dx squared plus y is equal to 0.001 x squared. Okay. And this one doesn't have any initial conditions, but I think we'll factor that in. Okay. Okay, so you can see here we have a non-homogeneous equation. So our right-hand side here is not 0. It is a function of x, and so that's good. So let's kind of run through our whole procedure here to get our full solution. Okay. Okay. So step 1, let's solve the homogeneous equation. So for the homogeneous equation, we're going to assume that the right-hand side is 0. Okay, so we're going to have d squared y dx squared plus y is equal to 0. Okay. So essentially, we're just, for now, we're ignoring the fact that the 0.001 x squared is present. So we're just setting that equal to 0. All right, so this equation here, we know how to solve. So let's form our characteristic equation. Okay, so we have lambda squared plus 1 is equal to 0. Okay. Here we can see lambda is equal to plus or minus I. So it is a situation where we have complex conjugate roots. Okay. So that means our homogeneous solution, we can just kind of skip to the end, is equal to C1 cosine of x plus C2 sine of x. Okay. All right. So I did that fairly quickly, but we've seen this so many times before. Any questions on up to this point in the problem? Okay. All right. So step 2. Let's go ahead and solve for the particular solution. Okay. All right, and then of course, we're going to be using the method of undetermined coefficients. Okay, so how does this work? And so from the problem, let me scroll up from the problem so you can see a bit again. Okay, from the problem, you can see that our non-homogeneous term is a second order polynomial, right? In other words, it's a quadratic function. And so if our non-homogeneous term is a polynomial of order 2, that means our particular solution should also be a polynomial of order 2. Okay. So you're literally just kind of looking and see what functional form the non-homogeneous term is, and then setting your particular solution to be the exact same form. Okay. And so here's how it works. And so, now that we know what functional form our particular solution is, we're going to guess that, except the coefficients of our guess are going to be undetermined because we're going to solve for them by plugging. So we're going to guess. Okay, so we're going to guess our YP takes the following form. So YP, okay. So we need to have a polynomial that goes up to order 2. So, but here's the thing with polynomials that, even though our non-homogeneous term only has x squared, we have to assume that our particular solution may have x squared, but it can also have every polynomial order up to that point. And so it may have x squared, it might have x, and they have a constant term as well. Okay. So let's do this. And so let's say that we're going to guess that our particular solution is k0 plus k1x plus k2x squared. Okay. So even if your non-homogeneous term doesn't have, if it's a polynomial and it doesn't have the linear term or the constant term, you have to include every single polynomial order up into that one. So polynomials are kind of unique in that sense, where you have to include all the lower order terms as well. Okay. Okay. So next thing we're going to do is we're going to take this guess and we're going to plug it back into our differential equation. And so what that's going to allow us to do is that it's going to allow us to solve, well, it's going to be able to, it's going to let us set up a system of equations to solve for all of these undetermined or unknown coefficients, K0, K1, K2. All right, and then once we solve for values for K0, K1, K2, and then at that point, our particular solution will be solved. Okay. Now, of course, in order to plug this into our differential equation, we have to take derivatives of this. Okay. So before we plug in, let's determine dyp dx. Okay. So we're just going to take the derivative of our functional form above. Okay. So taking the first order derivative of this, we get k1 plus 2k2x. Okay. And then we have d squared yp dx squared. That's equal to 2k2. Okay. So we're just taking the derivative of dy dx one more time. Okay. So now we have all this. Let's go ahead and plug it in, and I'll show you how you can solve for K1, K2, and K0 here. Okay. Okay, so let's go back to the original differential equation here. Okay, so our original differential equation, we're plugging in for everything with y, so everything on that side of the equation there. Okay, so first we have d squared y dx squared, and so we've already solved for that. That's 2k2. Okay, so we have 2k2 plus, right after d squared y dx squared, we have just y by itself. Okay, so we're going to plug in y, which is up there. Okay, so that's k0 plus k1x plus k2x squared. Okay, so this right here, this was d squared y dx squared plus y. Okay. So all I did was take our particular solution, or our guess for the particular solution, just plug it into the equation. Okay. And now we're going to set this equal to. So now we're not going to neglect the non-homogeneous term. So we're going to plug in for that. Okay. So our non-homogeneous term here is 0.001 x squared. Okay. All right, so after we plug in, next thing we're going to do is we're going to combine the like terms. And so we're going to combine terms according to the power of x that is next to. Okay. So first we have the constant term. So every term that's not multiplied by x. And so we have 2k2 plus k0. Okay. We have everything that's multiplied by x. So these are the linear terms. We have k1. Nothing else is multiplied by x. Okay. And then we have everything that's multiplied by x squared. And so I believe we only have one of those as well, which is just 1 times k2. k2 times x squared. And then all that's equal to 0.001 x squared. Okay, and so now that we have this relationship, we can just use the equation here to solve for the coefficients. Okay. First thing we notice is that there's only one term with x squared here, right? And so in order for this equation to be satisfied, K2 must be 0.001. Okay. Next thing that we notice is that there's only one term here on the left-hand side that's multiplied by x, but on the right-hand side, there's nothing, right? So K1 here must be 0 as well, okay? The other thing we have is that if we look at the constant term here, okay, there's no constant term on the right either. So that one must also be equal to 0 as well, okay? So if you can kind of see the patterns here into something simple like this, you can just kind of go based on the eye test. But something that I like to do, especially for more kind of complex situations where you have kind of multiple terms, is to kind of set up a system of equations based on the coefficients. Okay. All right, so we have 3 undetermined coefficients here. So we're going to need 3 equations. And so I'm going to make one equation for each of the terms. Okay. So I'm going to make an equation for x squared. I'm going to make an equation for x. And then for the constant term, I just put a 1 there. Okay. Okay, so let's do x squared first. So for x squared on the left-hand side, we have K2. On the right-hand side, we have 0.001, right? So those are all the coefficients for all of the x squared terms. And so you can see right away from that, K2 is going to be equal to 0.001. Next one that we have here is for x. And so on the left-hand side, we have K1 times x. On the right-hand side, we don't have any x terms, so that means K1 must be equal to 0. Okay. Okay. And then finally, for the last equation, for the constant term, we have 2K2 plus K0 on the left-hand side. And then on the right-hand side, we have nothing, because there's no constant term. So that means 2K2 plus K0 must equal to 0. Okay, so let's go ahead and solve this system here. So right away we see K2 is equal to 0.01. Okay. K1 is equal to 0, so that one's also very easy. But one thing that you would miss, or one thing that's easy to miss, is that K0 is actually going to be non-zero. Because if you look at this last equation, okay, from this last equation, we can solve it and say that K0 is equal to minus 2K2. And we know that K2 is non-zero, so K2 is 0.001. So that means K0 must be minus 0.002. All right, so let's plug in those values, and we can get our expression for YP. Okay, so YP, our particular solution in this case, is going to be 0.001 x squared minus 0.002. All right. Any questions on how we did that there? Okay, good. All right, so now that we have our homogeneous solution, now that we have our particular solution, let's just combine them together and form our full solution. Okay, so our full solution, y of x, is just going to be yh plus yp. Okay. And so it's going to be, let's plug in for yh. Yh was c1 cosine of x plus c2 sine of x plus 0.001 x squared minus 0.002. All right, and so that's the method. So you've probably seen this method before, and so hopefully this is kind of just a refresher. But as long as your non-homogeneous term falls into one of those three categories, so polynomial, exponential term, or sinusoid, you can deal with it with undetermined coefficients. Okay. Okay, so before we do the next example, let me go ahead and kind of write out the kind of what your guesses should be. Okay. Okay, so this right here will be kind of a table. So this is going to be a table for the starting guesses for your particular solution based on the form of your non-homogeneous term. Okay. So first we have exponential function. Okay. Okay, so on the left-hand side here, we have form of R of X. And on the right-hand side, we have guess for YP. Okay. Okay, so if you have an exponential function, your guess for YP is going to be an exponential with the same exponents, okay? Except there's an unknown coefficient out in front. So the guess here is going to be K e to the minus alpha x, or I guess alpha x. Usually the exponentials are going to be minus, but then sometimes you might have a positive too. So it's like K times e to the alpha x. Okay. Second one is a sinusoid, and so or excuse me, polynomial. My eyes read sinusoid, but I wrote down polynomial. So second one's polynomial. So we just did this one. Okay. So of course, you need to know the order of the polynomial. So this is of order n. Okay. Okay. So your guess for YP is going to be a polynomial up to that order n. So we have Kn, x to the n, plus Kn minus 1, x to the n minus 1, plus ... Okay. So theoretically, if you have a 10th order polynomial, that means your guess is going to have 10 terms, or excuse me, 11 terms. Okay. And so it's going to go all the way down to K2 x squared plus K1 x plus K0. Okay. So the polynomial one can kind of get out of hand very quickly if you have a very high order polynomial. All right, next we have sinusoids. Okay. So a sinusoid is either a sine or a cosine, okay, or both sometimes. So if your non-homogeneous term contains either a sine or a cosine, so it's either one or the other, your guess for YP has to include both sine and cosine. So I'll leave a note here. So even if your non-homogeneous term only has either one sine or one cosine, you have to include both. Okay. Now things get really messy if your non-homogeneous term has multiple sines and cosines of different frequencies. So the omega term is different. So let's say that your non-homogeneous term was cosine of x plus cosine of 2x plus cosine of 3x, right? So you have three different cosines of three different frequencies. In that case, your guess for YP is going to be K1 cosine of x plus K2 sine of x plus K3 cosine of 2x plus K4 sine of 2x plus K5 cosine of 3x plus K6 sine of, so it gets out of hand very quickly. Okay. But just know that if you're for a fixed cosine or sine of a given frequency, your guess for YP should be the same as. Okay. Okay. So those are the main ones. There's one more kind of special case, just because this does appear kind of very commonly for engineering applications. So the next one that we're going to do is a combination or the product of an exponential and a sinusoid. Okay. And so in those cases, your guess is going to be e to the alpha x multiplied by k1 cosine of omega x plus k2 sine of omega x. Again, you have to include both sine and cosine, but you just multiply your guess by the exponential out. Okay. Okay. Any questions on this so far? Okay. So a special case kind of comes up, when your homogeneous solution has the same functional form as your guess, or your guess for YP. Okay. So it could happen. And so, let's say that your functional form is an exponential that has the same exponent as your guess for YP, okay? Or maybe it's a sinusoid. So maybe you have a kind of a vibrating or an oscillating solution, and the frequency of your homogeneous solution matches that exactly with the non-homogeneous term, okay? So in this situation, you have to actually modify your guess. Because your particular solution must still be linearly independent from all of your from your homogeneous solution. Okay? So you can't have them be the exact same form. So you have to modify your particular solution. So our next example is going to cover this point exactly. And one of your homework problems is like this as well. All right, so how are we going to modify this, or what are we going to do? We're going to use the trick that we usually do, right? So if you think back to when we went over our repeated root, right? Kind of the trick that we did to make sure our second solution was independent from the first one was we kind of multiplied by x or multiplied by t. And so here we're just going to do the exact same. Okay? And so that goes for the polynomials, it goes for the exponentials and the sinusoids as well. Okay. Okay, so let's do an example that kind of shows this in action. Okay, so for this example, a little bit more complicated homogeneous form here. So we have d squared y dx squared plus 3 dy dx plus 2.25y is equal to minus 10 e to the minus 1.5 x. Okay. All right, and so just like we did in the last example, let's solve for the full solutions, homogeneous solution, particular solution, combine them together. Okay, I don't think I have it here, but let's also apply initial conditions on this as well, just so you can kind of see that done too. Okay. All right, I'll make up some initial conditions. Okay, so first step, just like the last example, let's go ahead and solve our homogeneous equation first. Okay. So we're going to take our differential equation there and form our characteristic equation. Okay. So you have lambda squared plus 3 lambda plus 2.25 is equal to 0. Okay. And so let's go ahead and plug this into our quadratic formula. So lambda 1 comma lambda 2 is equal to negative b, so negative 3 plus or minus square root b squared, so 3 squared minus 4 times AC, so 4 times 1 times 2.25. Okay. All divided by 2. Okay. So let's go ahead and evaluate the expression under the radical. So 3 squared is 9. 2.25 times 4 is also equal to 9. So we have 9 minus 9, which is 0. And so this term here goes away. Okay. And so what we have in this problem is we have a repeated root, okay, because we only have one root here, so it's minus 1.5. So that means our solution, or our homogeneous solution, will be an exponential function with that exponent, but one of them is going to be multiplied by x just to make it linearly independent. Okay, so that means yh of x is equal to c1 e to the minus 1.5x plus c2 x e to the minus 1.5x. Okay, so pretty straightforward so far. Okay. Any questions on how we got this homogeneous solution here? Okay, good. All right, step two. Step two, let's go ahead and form our particular solution. Okay. Okay, so let's go back to the problem, or let me just write it down here. Okay. So if we look at the non-homogeneous term in the original problem, it was minus 10 e to minus 1.5 x. Okay. So I just kind of repeated it here just for convenience. Okay. So we can see from this that our non-homogeneous term is an exponential function. So that means our yp, or our guess for yp, must also be an exponential function with the same exponent, right? So we're going to guess k e to the minus 1.5 x. Okay. All right. But we have a problem here, right? And so if we look at the form for our guess for yp, okay, it's an exponential function with an exponent of minus 1.5 x. Okay. If we look at our homogeneous solution, there's an exponent there with the exact same, or exponential term with the exact same exponent, right? So these are the same. So our particular solution can't be just e to the minus 1.5x. And so we have to make it independent from our homogeneous solution. Okay? So the way we do that is we're going to multiply this expression by x. So we're going to multiply by x. Great. So we've made it independent from that first term. But now our particular solution is x e to the minus 1.5x, right? If we look back at our homogeneous solution, we have that one too, right? So we can't have x e to the minus 1.5x. And so what do we do in this case? And so in this case, we just multiply by x one more time. And so now our guess for our particular solution is x squared e to the minus 1.5x. It's really kind of the you kind of just keep spamming x until you get something that's independent. You multiply by x, you ask, like, am I independent yet? Nope. Keep multiplying by x. Nope. Nope. And so you just keep doing it until you're independent. Luckily for second order equations, you'll probably not have to multiply by x more than twice, just because your homogeneous solution should only have two terms. But for higher order equations, which we're not going to do in this class, for higher order equations, you can keep multiplying by x if you want. Okay. Okay, so now we have our final guess for yp. So now we're at a point where we can actually take derivatives and plug it in. Okay. The issue now is that taking derivatives of this is going to be a little bit annoying because we do have to use product rule. So dyp dx. Okay. So let's take the first derivative here. Okay, so first derivative is going to be derivative of the first. So that's 2k x e to the minus 1.5x plus kx. Oops. Already messed up. So the second term here should be minus 1.5 kx squared e to the minus 1.5x. Okay. So that's the derivative of the exponential term after that. Okay. All right, and so then we're going to take the derivative one more time, and unfortunately we have to do product rule twice. So there is going to be four terms here, but just kind of make sure you're kind of keeping organized and seeing where everything comes from. Okay, so first term here we have 2k e to the minus 1.5x minus 1.5 times 2, which is 3k x e to the minus 1.5x. Okay. So both of these terms came from this one right here. Then we're going to take the derivative of the second one. So that's another minus 3kx e to the minus 1.5x. Okay. So that's the derivative of the first part of the second term. Plus we have a 1.5 times 1.5. So that's 2.25. 2.25 kx squared e to the minus 1.5x. So these two terms came from the second term. Okay. So before we plug this in, we can of course simplify this, and so those two terms in the middle can be combined together. And so we simplify this, we get 2k e to the minus 1.5x minus 6kx e to the minus 1.5x plus 2.25 kx squared e to the minus 1.5x. Okay. All right. Now the next step is to plug all of these guys into our original differential equation. All right, any questions on how we got here? Okay, good. Okay, so let's go ahead and plug in. Okay. So our original equation, let me just write out the original equation again. So we have d squared y dx squared plus 3 dy dx plus 2.25 y is equal to minus 10 e to the minus 1.5 x. Okay, so let's plug in. So first, let's plug in for d squared y dx squared. Okay, so that is conveniently right at the top of the screen there. We have 2k e to the minus 1.5 x minus 6k x e to the minus 1.5 x plus 2.25 kx squared e to the minus 1.5 x. Okay. All right, so that's our first term. Okay, let's plug in for the second term. So the second term is 3 times the first order derivative. So we're gonna have plus 3 multiplied by our first derivative, which was this guy up here. So let's go ahead and plug that in. So 3 times 2k, excuse me, 2kx, got the x. 3 times 2kx e to the minus 1.5 x minus 1.5 kx squared e to the minus 1.5 x. Okay. That is dy dx. And finally, we have 2.25 multiplied by y. And so our guess for yp, what started all, was kx squared e to the minus 1.5 x. Okay. Thankfully, that is that's the shortest one before all the product rule craziness kind of came into play. Okay. And all of this is equal to minus 10 e to the minus 1.5 x. Okay. All right. We have a lot of algebra to do, but luckily a lot of it is going to cancel out. So just like we did in the first example, let's take the left-hand side and let's combine the like terms. Okay, so first let me combine together all of the terms that are just multiplied by e to the minus 1.5 x. Okay. Okay, so the terms without any x's on them. Okay. Okay, so actually there should only be one term here if we did everything correctly. So it should just be this term. Okay. Because everything else should be multiplied by x. Yeah. Okay, so this term here is multiplied by 2k. Okay. Good. Okay, next let's find all the terms that are x e to the minus 1.5 x. Okay, so all of the x e to the 1.5 x, we have this one here, we have this one here, and that is it. Okay. So first there we have minus 6k, right, from the first term. Then the second term there, we have a plus 3 times 2, which is 6k. Okay. So we have minus 6k plus 6k, and so these two are going to cancel out, which is perfect, right? We don't have an x e to the minus 1.5x in our non-homogeneous term anyway, so that's good. All right, and then finally, we're going to sum up together all of the x squared e to the minus 1.5x terms. Okay, so let's use blue for this. Okay. So we have a positive 2.25k. We have a minus 3 times 1.5, and then a plus 2.5 here. Okay. Okay. So we do those. We have a positive 2.25 minus 3 times 1.5, which is a minus 4.5, plus positive 2.25. K, all times k, excuse me. Okay. So you have 2.25k minus 4.5k plus 2.25k. So all those, you add them up again are equal to 0. So that cancels out too. So that's good as well. Okay. So everything is coming together. Okay. And so after all the carnage, after all of the canceling out, all we're left with is e to the minus 1.5x, got the x there, times 2k is equal to minus 10 e to the minus 1.5x, right? So from this, we can see that 2k must equal to minus 10. Okay. Which means k is equal to minus 5. So all that worked for a fairly simple result. Okay. All right, so let's go ahead and plug that in. Okay, so that means yp must be equal to minus 5x squared e to the minus 1.5x. Okay. Then we can form our full solution. So our full solution, y of x, is equal to, first we have our homogeneous solution. We have c1 e to the minus 1.5x plus c2 x e to the minus 1.5x. Okay. Plus, or I should say minus 5x squared e to the minus 1.5x. Okay. And of course, that is our general solution. And so, we would have to apply initial conditions here to solve for C1 and C2. Okay. All right. Any questions on this? Okay, so we'll talk about resonance next time. Last thing I want to do right now is to show you, let me show you how to actually apply initial conditions to this. Okay. So when you're given a non-homogeneous problem with initial conditions, is that a question?
No.
Okay. So if you're given a non-homogeneous problem with initial conditions, you have to wait until your full solution before applying those initial conditions. So let me show you how to do that first. And then when we come back on Tuesday, first thing we'll talk about resonance. I know the instinct a lot of the times, just because that's how we did it before, is to apply the initial conditions after you solve the homogeneous problem, but you have to wait until the end to solve. Okay. Okay, so for this one, let's do some fairly simple initial conditions. So let's say we have y of 0 is equal to 10, okay? And we'll say that y prime of 0 is equal to 0, okay? So we have an initial solution, but our initial derivative is equal to 0. Okay, so now that we have our full solution here, let's go ahead and plug in. So let's plug in y of 0. Okay, so you have c1 e to the 0 plus c2 times 0 e to the 0 minus 5 0 squared e to the 0. Okay, all this must equal to 10, right? So right away you can see that the c2 term is going to go away. The particular solution is going to go away because we're plugging in 0. Okay. E to the 0 is just 1. And so we get C1 is equal to 10. Okay. Right. And then to apply the initial velocity, we need to take the derivative of y. Okay. So we have dy dx. Okay. So let me go ahead and scroll back up here so you can see it. It's a little bit hard. Okay. So again, we have to do some product rule here. It's unavoidable. Okay. All right, so we have derivative of the first term here. So that's a minus 1.5 c1 e to the minus 1.5x. Okay. Plus our second term, c2, we have to do product rule on this one. So we have a plus c2 e to the minus 1.5x minus 1.5 c2x e to the minus 1.5x. Okay. All right, so all of that comes from C2. And then for the last term, we again have to do some product rule here. We have a minus 10x e to the minus 1.5x. Okay. Minus 5 times 1.5 is 7.5. That's a minus plus 7.5 x squared e to the minus 1.5x. Okay. Okay, so let's plug in x is equal to 0. Okay. So we have a minus 1.5 c1 e to the 0 plus c2 e to the 0 minus 1.5 c2 times 0 times e to the 0 minus 10 times 0 e to the 0 plus 7.5 0 squared e to the 0. Okay. Keeping things simple, right? We're just applying a condition at x equals 0. According to our initial conditions for this problem, then this quantity right here is equal to 0. Okay. All right, so let's start canceling some terms. And so we can see here that this is multiplied by 0, so that goes away. This is multiplied by 0, that goes away. That's multiplied by 0 squared, so that super goes away. All of each of the zeros are going to go to 1. Okay. And so all we're left with is minus 1.5 c1 plus c2 is equal to 0. Okay. Or in other words, c2 is equal to 1.5 c1. Right. We know C1, so C1 that we just got from the first part here, we know C1 is equal to 10. So that means C2 is equal to 15. Okay. All right. So now that we formed our full solution here, we can go ahead and plug everything back in. So our full solution with the boundary conditions is equal to y of x is equal to 10 e to the minus 1.5x plus 15 x e to the minus 1.5 x minus 5x squared e to the minus 1.5 x. Okay. Remember, you can't do this until you have the full solution with the particular solutions. Okay. All right. Any questions on how we got this result here? Okay. All right. So we'll end a little bit early today, just because can't really do much in 3 minutes. And so when we come back on Tuesday, there's one last topic I want to go over with second order equations, which is resonance, which is a very, very important phenomenon, especially for engineers. And so, definitely make sure, you get that. And then we're going to move on to probably the first new topic for most of you, which are Laplace transforms. Okay. All right. So thank you guys for coming today. I hope you guys have a good weekend. Stay dry. I think it's going to rain for the rest of the weekend. And I'll see you guys on Tuesday. Thanks, Joel.
Why I got a 580.
I think when it might have been either, can you open up the PDF that was submitted? Yeah, I only got one problem.
Oh.
Yeah, so if you want to resubmit, do you want to email it?
Okay, yeah, I have it. I think it's, it'll show that I did it before.
Yeah, just email it to me. I'll revise it.
Yeah,
I'll
okay.
revise it. Yeah.
Okay.
Mhm.
Email it to?
Yeah.
Okay.
Mhm.
Oh, sure, I see we could go up.
Yeah.
But a little bit. I think right
Right here?
a month. Or, before we got the solution, everything.
All right.
And then can you go over, sorry, the lecture? So I kind of missed the,
Oh, sure.
kind of missed like the first lecture.
Sure. Yeah, so it started right here. Yeah.
Thank you.
Mhm.
I appreciate it. You do good, Professor.
Yeah, you too.
You have a good one.
You too.